right, so let's start by going over the topics that are going to be on the exam. 2.1 is pretty safe to say, right? That's going to be on there. And the things that we had out of 2.1, right? The area between curves. Right, so we had integrals dx and we had integrals dy, depending on which, what the setup was for the region that you want to find the area of. So, basically anything from 2.1 is fair game. Good afternoon. All right, so then 2.2, that's where we had, I think, two different things. Well, I mean, that's where we had the volume by slicing. Okay. And those were, volume is the integral of some area function, right? Where maybe we're given the cross sections or something like that. Okay. So we'll have a question like that on the exam, and it should look familiar to something that we've seen before, either out of the homework or off the quiz. Okay. 2.3 was volume using. I think in 2.2 that we also had the disk and washer method. And then in 2.3, we had the shell method. Okay. Basically, you're just going to have one question where it's going to be one or the other. Okay. And depending on the region that you get, sometimes you can use one or the other depending on how you want to set it up. And both of them are viable. And that's what we saw on the quiz too. Okay. 2.4 was arc length and surface area. Okay, so let me be specific. Surface area is not going to be on the exam. And for arc length, this formula, right, for arc length will be given on an arc length problem. So you don't have to remember it. Okay. 2.5 was work, and we had three different types of work problems, right? We had springs, we had pumping water, and then we had lifting a chain. And there were variations on the, well, I mean, springs are always springs, but there were variations on these also, but I think that pretty much encompasses everything that was in that section. Um, the lifting a chain and the springs won't be covered. You'll just have one with pumping water. Okay. 2.6 was moments and center of mass. So on this one, you'll have one center of mass problem. where the formula for x bar, y bar, those will be given. Maybe I should write down exactly what will be given. Okay, so here's the formulas for center of mass, really, right? So we have the we have the mass equation. We have the mass equation, and then we have the actual centers at x bar, y bar, where x bar is my over m, y bar is mx over m, and we have with mx and my are. Okay. So you don't try to, you don't have to remember all the nitty gritty details here, but you have to know how to set it up and evaluate an integral. Okay. That one I think is usually a little bit more straightforward, right? If you've practiced some, you know how to set it up. They're typically not as tricky as like the integrals that you can get with arc length. All right. In 2.7, that was like kind of a review almost of Calculus 1, where we took exponentials and logs and we did integrals with them. Okay, and this is maybe a little bit redundant with 2.8. So you're not going to have a question that specifically says integrate these exponentials and logs. Instead, what you're going to do is get an application question from 2.8 and then have to do something with that, right? Okay, so instead, you'll just get something out of 2.8 that where you might have to involve a derivative or an integral. Okay, and I'm not going to give you the equation you need to know. The p equals p0 e to the kt, or if you use different variable names, that's fine, but you have to have the general idea of what an exponential growth function looks like. Okay, and I thought about this for a little while. 2.9 hyperbolic functions. I'm just going to not put this on the exam. And my reasoning for that isn't that this isn't something that's doable or that it's something, that would be too difficult or anything like that. The problem with the hyperbolic functions is you get kind of like this little brief glimpse into this big area. There's a lot of stuff to learn there. And I think that the trouble is, from a student perspective, you can spend an awful lot of time studying stuff because there's a lot there. and then you get like this one question, and of course it's not going to cover everything, you know, in that section. There's just a lot of stuff in that section. And the stuff that we learn in that section isn't super essential to what we're doing next, so much so that you need to have studied it really hard. It's something that I'm glad that we covered and we talked about a little bit. We'll take a look at how it comes up in, you know, when we're doing stuff in chapter 3. But it's not super vital, so we're just not going to have that on the exam. All right. So that gives you kind of an overview of what's going to be on the exam. Now you know a little bit better what to look at and what not to. Would you like to go over some sample problems? I said, would you? Which sample problems I think should we focus our attention on? For 2.7, so the idea is that integrals of exponentials and logs sometimes come up in section 2.8. So when I say it's not specifically on the exam, what I mean is you won't have a question that says, take the integral of this, right? It's just that, you know, you end up using it in 2.8. So it'll just be one question that'll cover both, I guess. So your question, how many questions will be on the exam and how much time will you have to complete it? Well, you'll have a regular class period, right? So you'll have 75-minute class period. That's all that we're going to do on Monday. You'll show up, have the exam. When you're done, you're done, right? So you get the full period, but it's just the one period. As far as how many questions, I'm still going back through it. I need to make sure that it's not too long. So I haven't finished sort of editing it yet. But to give you a rough idea, like single digits, right? Somewhere in like, you know, 7 to 9 question range, depending on. Sometimes I rearrange it so that there's fewer questions and one of them has more parts. And sometimes I say, oh, never mind the parts, we'll just break this into separate questions. And I haven't finished that breakdown yet, so. But that gives you an idea, something like 7 to 9 questions. There's a little bit of a delicate balance there, right? So you definitely don't want an exam too long, but I have given exams that are only like 5 questions, and sometimes it makes people nervous because it's like, if you don't know how to answer a question, one question is like 2 letter grades, so it feels like every single one of them you have to know. And there is partial credit, but the idea is that it can be a little higher stress if you mess something up. So I don't know. But as I said before, my goal in the exam is to not have any surprises. I can be very creative writing questions, and never during an exam. I make my exam questions very boring. There's stuff that you've seen before. Looks like the homework questions or the quiz questions. So no, should be no surprises. Okay, so maybe rather than answer one question off the quiz, maybe we should just go through the whole quiz. This is probably a good time to do that. So I'm just going to go through each one of these. First one, find the length of the curve y equals x to the 3/2 from x equals 1 to x equals 4. You have to evaluate the integral here. So let's start by writing down our formula. I think that I gave this to you on the board. On the exam, I'll just write these on the exam. I just forgot to do it for this one. The integral from a to b of the square root of 1 plus f prime of x squared dx. That's our formula for arc length. What I like to do with these questions is to go step by step. This is an easy function to work with, so you're maybe tempted, oh, I can do derivative in my head. I know how to square things in my head. I can add 1 in my head. And those may be true, but when you try to do all of those at once, you might get it right, or you might leave something out. And, you know, it's worth writing things down as you go. So I'm going to start by saying, okay, f is x to the 3/2. Then I take the derivative f prime, 3/2 x to the 1/2. Then I take f prime and I square it. So it's multiplied, so I'm just going to square each piece. So we get 9/4 x to the 1/2 squared will just give me to the power of 1. So then 1 plus f prime squared is 1 plus 9/4 x. Okay, so that's what goes inside the square root in my integral, right? So I'm going to have an integral. It gives me the limits, right, from x equals 1 to 4. I'm integrating the square root of 1 plus 9/4 x dx. The way that I'm going to integrate this is I'm going to use a u substitution. Let u equal 1 plus 9/4 x. Then the u dx is 9/4. So I'm going to do 2 steps here. I'm going to multiply both sides by dx and divide by 9/4, right? So 4/9 du equals dx. Okay. Since I have a definite integral, I'm going to go ahead and also change my limits of integration over. So when x is 1, u is 1 plus 9/4 times 1, which is 1 plus 9/4 or 13/4. When x is 4, u is 1 plus 9/4 times 4. 4's cancel, 9 plus 1 is 10. So I'm going to go from these x values to a set of u values. Okay. And I'm now integrating, the whole inside is just a u, and then the dx is going to become a 4/9 du. Okay, so we're going to take a couple steps here. The 4/9 I can factor out. And the u I'm going to write, or the square root of u I'm going to write as a u to the 1/2 power. Okay, so now I know that when I integrate, I can use the power rule. I add 1 to the power, divide by the new power, or multiply by its reciprocal. I like to keep writing, especially in a problem where a variable has changed. I like to keep track of what variable my limits of integration are the whole time. It's just a good habit that I use to avoid making mistakes. Okay, 4 times 2 is 8. 9 times 3 is 27. And we have u to the 3/2. I'm going to plug in the 10, so I have 10 to the 3/2 minus 13/4 to the 3/2. Okay, now this is a perfectly fine number. If you want to throw it in a calculator and get a decimal approximation, that's fine. But I'm perfectly happy with, and would maybe even almost prefer just leave it as an exact answer. But just for reference, maybe we'll multiply this out. Oops, so 13/4. Okay, so as a decimal, this comes out to about 7.6337. Okay, and if I want to know if that seems reasonable, we're looking at a curve that's going from x equals 1 to x equals 4. So in the x direction, we're moving over by 3. So the length has to be definitely bigger than 3. And depending on how curvy it goes, that's going to be how much extra we do, right? So if I look at a graph, y equals x to the 3/2. Right. So from 1 to 4, I can see It's moving up pretty far, so and maybe it makes sense that, you know, a little more than double 3. Okay, so it seems reasonable. Okay, so do you have to change the limits of integration? You don't really have to. So I could have alternately, let me just do this sort of separately over here. I could have left my limits of integration as x equals, going from 1 to 4, and still integrated with the u's, right? So square root of u times 4/9 du, right? I do the integration, right? So we get the 8/27 u to the 3/2. But these are still x values, and I can't plug x values into u. So what I do is I say, okay, let's go back to x's. So I can replace the u with 1 plus 9/4 x. And now I say, oh, okay, these are x values. I can plug x in for x, and that's fine. So I plug in 9. I'm sorry, plug in 4. And I plug in 1. Okay. And if you look at what I have here, it's going to be the same number. Okay. So yeah, whatever way you're comfortable with, if you like changing your limits of integration over, do it. If you'd rather just, integrate and then go back to x's and plug the x values in, then do that. It doesn't really matter. I think a lot of people like the changing the limits of integration because it seems a little faster. It seems like you're saving a step at the end. In the next chapter, we'll look at some problems where you're kind of stuck doing it the other way, where you have to, there'll be a lot of problems where there's too many crazy substitutions to keep track of your limits of integration. So you just have to go back to your original x's and then plug in anyway. Because trying to change your limits gets too crazy. Okay. So let's look at problem 2. How old is a skull that contains 1/5 as much radiocarbon as a modern skull? Note that the half-life of radiocarbon is 5,730 years. So I don't know how much radiocarbon is in a skull, but I do know that this is going to have 1/5 of the amount that it started with. Okay, so that's what we're working off of. Before I start talking about the skulls, let's just look at the radiocarbon on its own. Okay, the half-life is enough information for me to get the growth constant. So what we do is we say, okay, if I use my formula for exponential growth and decay, if I want half-life, what that means is that at some point in time, which is 5,730 years later, I'm going to have half as much as what I started with. So I'm going to have half as much of my initial value when I plug in t is 5,730. So if I just divide both sides by p0, right, they completely cancel away and that's gone. So half of my, half equals e to the k times 5,730, and then we take the natural log of both sides. When you take natural log of e to the stuff, the exponential and the log cancel, and we just get k times 5,730. Okay, so k is just ln of 1/2 divided by 5,730. Okay. This is also 1/2 is 2 to the negative 1, and in logs you could take a power and bring it out front. So this is the same as negative ln of 2 over 5,730. Okay. If you want that as a decimal, you can write it out. ln of a half divided by 5,730. Okay, but I feel like the decimal is more work to write out than just writing out the exact value. So even if I'm going to use my calculator, I'm just going to use the exact value. Okay. When I'm doing my work for this problem, though, I'm just going to keep writing k. I know what k is, but this is kind of a pain to write as an exponent, and I don't want to get confused. All right, so let's go ahead and look at skulls now. We have a skull that has 1/5 as much radiocarbon as a modern skull. So we have 1/5 of the starting amount. Oh, the homework videos are different. Yeah, that's all right. So we have 1/5 of the starting amount. So if I just divide, again, by P0, I get 1/5 equals e to the kt. And then I can use logs. And then I divide by my k. Okay, now remember, k we have a value for. I didn't write it down just because it's, it's this big mess. Okay, but if I want to enter it in my calculator, I can. So I get up my calculator, and we say, all right, we have ln of 1/5, and I'm going to divide it, and now I'm going to put this other fraction in parentheses. I have ln of 1/2 divided by 5,730. Okay, so then we get a number out, and that's the number of years, right? So 13,304.65. Oops, 13,304. Okay. All right, any questions on this one? Okay, let's look at problem 3. Find the work required to pump all the water out of a cylinder that has a circular base of radius 2 meters, height of 20 meters, and is 3/4 full of water. Okay, so I'm just going to draw a diagram. Okay, so this radius is 2, and that's the same radius throughout the whole thing. So cylinders are actually kind of nice. Okay, the height is 20. It's 3/4 full of water. Okay, and we want to first create an integral and then evaluate it that pumps all of the water out. So the idea is if I take one slice of water here, okay, that's all going to be moving the same distance out. So let's figure out the work required for one slice. Oops. Okay, so work is force times distance. Okay, distance part is easy. Let's do that first. I need to put in a variable to measure stuff. I'll just use x, but you could also use like h for height or whatever variable you like. And you could also have it, measure going down or measure going up. Again, that's up to you. It'll make things look differently. But the way that I've set up problems so far in the class is I always, put it at the bottom measuring up. So that'll be what x measures, right? So at the bottom is x equals 0. Okay, so if I want to find the distance that we have to pump the water out, this whole length is 20. If I take away x, I'll get this purple piece. So this is 20 minus x. Okay. All right, the force is the force of gravity. So this says the gravitational constant is 9.8 newtons per kilogram. So I have to take that 9.8 newtons per kilogram and multiply by how many kilograms I have. So I'm going to multiply by the mass. Okay. The mass says the density of water is 1,000 kilograms per cubic meter. So the mass is going to be 1,000 kilograms per meter cubed. I have to multiply by volume to cancel out those meter cubed, right? So one way to do physics is just follow the units, right? If I want to end up with force, I have 9.8 newtons over kilograms. If I cancel the kilograms, I'll have a force in newtons, right? If I want kilograms and I have a kilogram over meter cubed, multiply by meters cubed, right, which is a volume. Okay, so I need to find the volume of one of these slices. The volume, what I have is a a flat pancake shape, but it is a cylinder, right? The radius r, and it has a thickness on it. That's a small change in x, right? So we'll use delta x for the thickness. So for a cylinder, we get pi r squared h, or pi r squared times delta x. Now, I don't really want to have an r as well as x variables. That's too many variables. So we have to figure out what r is, right, as a function of x. And for most of our problems, it's actually been a function of x. But in this case, the radius of 2 stays the same the whole way up. So we can just plug in our 2 there. Okay, so we just get 4 pi times delta x. Okay. So then that's the volume that I plug in here. So here we get 1,000 times 4 pi delta x, or 4,000 pi delta x. Okay, that's the mass, so I plug that in here. We get 9.8 times 4,000 pi delta x. Which is 39,200 pi delta x. Okay, and work is force times distance, right? So I'm going to take that and multiply by my distance, 20 minus x. Okay, so this is for one slice. So now the total work I'm going to add up all of my slices, right? So we have that 39,200 pi. I'll just rearrange terms so that the delta x is at the end. So I add up all of my slices, then I take a limit as the number of slices goes to infinity, and that gives me an integral, 39,200 pi times 20 minus x dx. Okay. I need to figure out my limits of integration, though. Where do the slices start and where do they stop? I want to pump all of the water out. Okay, so I'm gonna do all of the existing water, so my x is going to start at 0. And it says that it's 3/4 full. Full would be its value of 20, so 3/4 full times 20 will give me 15, right? So we just go up to 15 meters. Okay, so we have to evaluate the integral, but that's an easy enough integral. I'm just integrating 20 minus x dx from 0 to 15 with that big messy constant out front. So when I integrate, I get 20x minus 1/2 x squared. So we get 20 times 15 minus 15 squared over 2, and then subtract 0, right? Because I plug in 0, I'll get 0. Okay. So this comes out to, I think that's 7,350,000. Okay, in my units of work. And you know, if you remember your units and you tack that on, great. And if you don't, then you know, I'm not going to dock you here. If you were in a physics class, though, you better have your units on. Units are probably more important than the number in a physics class. Okay, so. Oh, and I'm glad I left space for it. I didn't multiply in the pi. Pi's still out there. All right. Any questions on that one? Okay. All right. So, I mean, this isn't really an accident, but you know, the quiz is kind of gives you a nice review because this is out of the work section. This is the type of problem that we'll be looking at, right? The pumping water, right? We have to build the integral first. There's something out of 2.8, right? And then something out of arc length. What was that? 2.5. I don't remember. But anyway, these are all things that you know, on our list we said we're going to be covered on the exam. So this is a good set of problems to review.